So good day. Today we're going to solve some problem in refrigeration and air conditioning. Problem 3 to 5. A cooling tower is a device that cools a spray of water by passing it through a stream of air. If a 15 meter cube per second of air at 35 degrees Celsius dry bulb and 24 degrees Celsius wet bulb temperature and an atmospheric pressure of 101 kilopascal enters the tower and the air leaves saturated at 31 degrees Celsius, to what temperature can this stream cool a spray of water entering at 38 degrees Celsius with a flow rate of 20 kg per second, and how many kg per second of makeup water must be added to compensate for the water that is evaporated? So we have given your volume flow rate, which is 15 meter cube per second, your T1, which is 38 degrees Celsius, and your mass of your water, which is 20 kg per second. So at 35 degrees Celsius dry bulb, 24 degrees Celsius wet bulb, so using our psychometric chart, we could able to find the value of your enthalpy, specific volume, and our humidity ratio. So just we say 35 degrees Celsius. Here is our 35 degrees Celsius and your 24 wet bulb. So it gives us a value of 70 plus approximately, and our specific volume, which is 0.0, since it is above your 0.88, 0.89 point something approximately, and our humidity ratio, it is 0.14 or approximately over 0.143 or 4, something like that. So we have here your H1, which is 71.60 kilojoule per kilogram, our specific volume, which is 0.89, 280 meter cube per kilogram, our weight, which is 0.0143 kilogram per kilogram. So at 31 degrees Celsius saturated, table A2, so from the book, from our table A2, we have here our 31 degrees Celsius, the value of our H2, which is 105.337, and the value of our humidity ratio is 0.02900 kilogram per kilogram. So required is our T2 and the makeup mass of water. So by finding the formula of your mass using your conservation of energy of mass, volume flow rate divided by your specific volume is equals to 15 meter cube per second times 0.8920 meter cube per kilogram equals to 16.80 kilogram per second. So by solving of your T2, we have your mass of your water times your constant pressures of water times your TW1 minus your T2 or TW2 equals to your mass times your change, the difference of your enthalpy. So by substituting the given value, we have 20 kg per second times 4.19 kilojoule per kilogram Kelvin times 38 degrees Celsius minus T2 equals to 16.80 kilogram per second times the difference of your enthalpy, which is 105 minus 71.60 kilojoule per kilogram. So it gives us a value of your T2, which is 31.30 degrees Celsius. So for solving for your makeup mass of water, so equals to your mass times your change in humidity ratio. So makeup mass of water equals to 16.80 kilogram per second times 0.0290 minus 0.0143 kilojoule per kilogram per kilogram. So cancel out. Our unit is kilogram per second. So the answer is 0.247 kilogram per second. So for problem 3 to 6, in an air conditioning unit, 3.5 meter cube per second of air at 27 degrees Celsius dry bulb temperature, 50% relative humidity, and standard atmospheric pressure enters the unit. The living condition of the air is 13 degrees Celsius dry bulb temperature and 90% relative humidity. Using properties from the psychometric chart, calculate the refrigerating capacity in kilowatts and determine the rate of water removal from the air. So given, we have your volume flow rate equals to 3.5 meter cube per second. So at 27 degrees Celsius, dry bulb, 50% relative humidity. Using your psychometric chart, we could able to find the value of our enthalpy, specific volume, and the humidity ratio. So we have 27 degrees Celsius. Here's your 27 degrees Celsius. And our relative humidity, which is 50%. So 750. So by projecting it to your enthalpy, I think it will give us a 55 point something, approximately 55 kilojoule per kilogram. So sobra lang 55. Then for our specific volume, we have 27 and your 50% relative humidity. So since ibabaw lang sa 0.86, kung makita naton, it gives us an 0.86 500 point something approximately. So for our humidity ratio, since it is at the center of 0.10 and 0.12, just we say it is 0.1011. So next, at 13 degrees Celsius dry bulb, 90% relative humidity, using our psychometric chart, we could able to find the value of our enthalpy 2 and our humidity ratio 2. So 13 degrees Celsius here and 90% relative humidity here. So looking for our H2, it gives us 34 kilojoule per kilogram, since wala sa nakasampot sa 35. And our humidity ratio, which is i-project natin siya dire, sobra lang sa 0.0 0.084 kilogram per kilogram. So here for our enthalpy 2, which is 34 kilojoule per kilogram, and your humidity ratio, which is 0.0084 kilogram per kilogram. So solving for our mass, we have volume flow rate divided by your specific volume. So 3.5 meter cube per second divided by your 0.86530 meter cube per kilogram, it gives us an answer of 4.045 kilogram per second. So for solving for refrigerating capacity, your QE is equals to your mass times your change in enthalpy is equals to your 4.045 kilogram per second times 55.311 minus 34 kilojoule per kilogram. So cancel out your kilogram. So kilojoule per second. So the final answer is 86.20 kilojoule per second or kilowatt. So solving for rate of your water removal is equals to your mass times your change in your humidity ratio equals to your 4.045 kilogram per second times 0.011 kilogram per kilogram minus 0.0084 kilogram per kilogram. So it gives us an answer of 0.0113 kilogram per second. Problem 3 to 7. A stream of outdoor air is mixed with a stream of return air in an air conditioning system that operates at 101 kPa pressure. The flow rate of outdoor air is 2 kg per second and its condition is 35 degrees Celsius dry bulb temperature and 25 degrees Celsius wet bulb temperature. The flow rate of return air is 3 kg per second and its condition is 24 degrees Celsius and 50% relative humidity. Determine the enthalpy of the mixture, the humidity ratio of the mixture, the dry bulb temperature of the mixture from the properties determined in parts A and B and C. The dry bulb temperature by weighted average of the dry bulb temperature of the entering stream. So, solution, using psychometric chart at 35 degrees Celsius dry bulb and with 24 degrees Celsius wet bulb. So, using our psychometric chart, we could able to find the value of your enthalpy and your humidity ratio. So, here's the dry bulb temperature, which is 35 degrees Celsius, and your wet bulb, which is this diagonal curved line is your relative humidity, which is 24. So by these intersections, it gives us an value of 75 point, approximate to 75.7 kilojoule per kilogram. And by finding the humidity ratio at 35 and 24, it gives us a value of 0.015159, approximate to 0.016.0159 kilogram per kilogram. So at 24 degrees Celsius dry bulb and with 50% relative humidity, so we could able to find the value of your enthalpy 2 and your humidity ratio 2. So by projecting by using our psychrometric chart, so 24 degrees Celsius here and our relative humidity, which is 50%, so we could able to find your enthalpy. So 24 and 50, it gives us an approximate to 47 point something, and 24 and 50 with relative humidity, it gives us a value of 0.009 approximate. So by solving, your enthalpy of your mixture, M1 plus M2 equals to your enthalpy 1 times your mass 1, plus your enthalpy 2 times your mass 2 equals to, by deriving the equation, we have enthalpy of your mixture equals to your H1 M1 plus H2 M2 divided by M1 plus M2. So by substituting the given, we have enthalpy of your mixture equals to 2 kg per second times 75.7 kilojoule per kilogram plus 3 kg per second times 47.520 kilojoule per kilogram divided by 2 kg per second plus 3 kg per second, and it gives us an answer of your enthalpy mixture equals to 58.78 kilojoule per kilogram. So by solving of your humidity ratio, the mixture, we have humidity ratio of your mixture times your M1 plus your M2, or your mass 1 plus your mass 2 equals to your mass 1 times humidity ratio 1 plus mass 2 times your humidity ratio 2. So humidity ratio of your mixture equals to your M1 times W1 plus M2, W2 divided by M1 plus M2. So by substituting the given value, we have 2 kg per second times 0.015 kg per kilogram plus 3 kg per second times 0.0092 kg per kilogram divided by 2 kg per second plus 3 kg per second. It gives us an answer of 0.00194 kg per kilogram. So for dry bulb temperature at 58.78 kilojoule per kilogram from the from our enthalpy mixture and from our humidity ratio, which is 0.1194 kilogram per kilogram. So from using psychrometric chart, we could able to find the value of our dry bulb temperature. So we have here a 58.78 and 0.1194. So here, by projecting 58.78 and our 0.1194 here, so it gives us a value of approximate to 28, 25, 26, 27, 28 point something. So our dry bulb temperature is 28.6 degrees Celsius. From our solving for our temperature mixture, so times your mass 1 plus your mass 2 equals to your T1 times M1 plus T2 times M2. So from deriving the formula, we have temperature of your mixture equals to T1 M1 plus T2 M2 divided by your M1 plus M2. So from the given from the given value, so let's substitute the formula. We have 2 kg per second times 35 degrees Celsius plus 3 kg per second times your 24 degrees Celsius, divide 2 kg per second plus 3 kg per second. So it gives us a value of 28.4 degrees Celsius. Problem 3 to 8. The air condition at the intake of an air compressor are 28 degrees Celsius, 50% relative humidity, and 101 kPa. The air is compressed to 400 kilopascal or kPa, then sent to intercooled. If condensation of water vapor from the compressed air is to be prevented, what is the minimum temperature to which the air can be cooled in the intercooled? So, what is asked here in the problem is your dew point temperature. So, at 28 degrees Celsius, our saturation pressure is 3.778 kilopascal. So from your table here, table A1, which is water properties of liquid and saturated vapor, our 28 degrees Celsius has a value of 3.778 kilopascal, our saturation pressure. So at 50% relative humidity, so our saturation pressure times 0.5 times 3.778 kPa, so equals to 1.889 kilopascal. So our PT is equals to your 101 kilopascal. So from the formula of your humidity ratio is equals to your 0.622 times your saturation pressure divided by your PT minus saturation pressure. So your humidity ratio is equals to your 0.622. We have here your 1.889 kilopascal divided by the difference of your PT minus PB, which is 101 minus 1.889 kilopascal. So it gives us an answer of 0.01186 kilogram per kilogram. So at 400 kilopascal, by solving the saturation pressure at 400 kilopascal, so using the formula of your humidity ratio as well, we have here the value of your humidity ratio, which is 0.01186 kilogram per kilogram. We're going to use your humidity ratio in solving our saturation pressure at 400 kilopascal. So is equals to your 0.622, the constant, times your saturation pressure over 400 kilopascal minus your saturation pressure. So by solving algebraically, so it gives you an answer of 7.4812 kilopascal. So from table A1, we could find our dew point or our temperature. So 7.4812. So here from the table of your water, your properties of liquid and saturated vapor, so we have 7.4812. So it naglapaw lang it gamay. So butang naton nga 40 point something ang aton nga temperature. So 40.4 degrees Celsius approximate. Problem 3 to 9. A winter air conditioning system adds for humidification 0.0025 kg per second of saturated steam at 101 kPa or kilopascal pressure to an airflow of 0.36 kg per second. The air initially at a temperature of 15 degrees Celsius with a relative humidity of 20%. What are the dry and wet bulb temperature of the air leaving the humidifier? So solution, at 15 degrees Celsius with a 20% relative humidity, so by using your psychometric chart, 15 degree Celsius your dry bulb and 20% relative humidity. So here is a relative humidity 20%. So it gives us an answer a value of your enthalpy, which is 20 point something approximate. So do lapit-lapit siya sa 20, so 20 point something. And our humidity ratio, so i-project na itong pagilid, so it gives us a value of 0.002. So enthalpy 20.021 kilojoule per kilogram, and our humidity ratio is 0.002 kilogram per kilogram. So at 101 kilopascal steam, our enthalpy at vapor is 2675.85 kilojoule per kilogram. So from our table here, we have 101 kilopascal. So we have here an approximate value of enthalpy, which is 2676.0 kilojoule per kilogram in vapor. So we have here the answer of 2675.85 kilojoule per kilogram. Our mass of water vapor, which is 0.0025 kilogram per second, and our mass, which is 0.36, and our by solving the value of your humidity ratio 2, so using this formula, we have your mass of water vapor equals to your mass times your humidity ratio 2 minus humidity ratio 1. So 0.0025 kilogram per second is equals to your 0.36 kilogram per second times your humidity ratio 2 minus 0.002. So by solving, mathematically, it gives you an answer of 0.00894 kilogram per kilogram. So by solving of your enthalpy 2, so your mass times your change in enthalpy equals to your mass of your water vapor times your enthalpy of your vapor. We have 0.36 kilogram per second times your H2 minus 20.021 kilojoule per kilogram equals to 0.0025 kilogram per second times your 2675.85 kilojoule per kilogram. By distribution, 0.36 times H2, 0.36 times 20.021, so 7.27756 kilojoule per kilogram equals to your, by multiplying, 6.689625 kilojoule per kilogram. So our value for our H2 or your enthalpy is equals to your 38.60 kilojoule per kilogram. So using psychometric chart, we could able to find the value of our dry bulb temperature and wet bulb temperature using the given using the enthalpy and our humidity ratio. Our answer above, we could able to find the dry bulb and wet bulb using your psychometric chart. So our enthalpy, which is 38.6, so here's 38.6, 38, and our humidity ratio, which is 0.0894, so approximate to here 0.008, 0.009. So the value of our dry bulb, I think approximate to 16 point something, and our wet bulb, since it is at the center of your 10 and 15, in between of your 10 and 15 degrees Celsius, let's see, 11, 12, 13, it is approximate to 13 point something. So the value of our dry bulb temperature is 16.3 degrees Celsius, and our wet bulb is 13.9 degrees Celsius. Problem 3 to 10. Determine for the three cases listed below the magnitude in watts and the direction of transfer of sensible heat using the equation 3 to 8, latent heat using equation 3 to 9, and the total heat using equation 3 to 14. The area is 0.15 meters squared, and the HC or your convection coefficient is equals to your 30 watts per meter squared, the times your Kelvin, your air at 30 degrees Celsius and 50% relative humidity is in contact with water that is at a temperature of A, 13 degrees Celsius, B, 20 degrees Celsius, and C, 28 degrees Celsius. So, solution from equation 3 to 8 using sensible heat. So, from the equation in the book, we have here the rate of your sensible heat is equals to your convection coefficient times your area, and the difference of the temperature between the air and the weighted surface, weighted surface, or your TI. Next, from equation 3 to 9, your latent heat formula, we have here your rate of your mass heat transfer is equals to your proportionality constant times your area, and times your rate of your humidity ratio, in humidity ratio of air and weighted surface, times your enthalpy of your latent heat. Next, your equation 3 to 14 or your total heat, so equals to your convection coefficient times your area divided by your specific heat of your moist air times your change of the difference of your enthalpy of your air and enthalpy of your weighted surface. So we have here the given, which is our convection coefficient, which is 30 watts per meter squared Kelvin, times your and area, which is 0.15 meters squared. So using your psychometric chart, here we have 30 degrees Celsius and 50% relative humidity. So here is our dry bulb, 30 degrees Celsius and 50% relative humidity. So it gives us a value of 65, approximate to 65 point something kilojoule per kilogram, and our humidity ratio, which is 0.013 approximately. So it gives us a value of 0.0135 and 64 kilojoule per kilogram. So at 13 degrees Celsius, from our letter A, solving for your sensible heat using the formula of your sensible heat, we have here your convection coefficient times your area times your change in your temperature. So we have 30 watts per meter squared times Kelvin divided by your 0.15 meters squared divide times 0.15 meters squared times your 13 minus 30 degrees Celsius. So why ni? So cancel ang aton nga Kelvin. So 13 degrees Celsius i-plus na to 73, and our 30 degrees Celsius add na to 73. It gives us the same value when we difference kung i-minus nato ang 13 kag 30. So it gives us also a negative 17 degrees Celsius. So negative 17 times 0.15 meters squared times 30 watts per meter squared. So it gives us a value of negative 76.5 watts. So cancel meter squared. So from your humidity ratio at 13 degrees Celsius equals to 0.0937 kilogram per kilogram from table A to 2. So from table A to 2 moist air, you have 13 degrees Celsius, which is 0.00937 kilogram per kilogram. So for our latent heat, we have enthalpy at 13 degrees Celsius is equals to 2470.840 kilojoule per kilogram. So it is using your steam table from your 13 degrees Celsius. It gives you an HFG of 2470.7 kilojoule per kilogram. So next, from your proportionality constant is equals to your convection coefficient, divide your specific heat of your moist air, which is 1020 kilojoule per kilogram Kelvin. So HD is equals to your 30 watts per meter squared Kelvin divided by 1020 kilojoule per kilogram Kelvin equals to your 0.029412 kilogram per meter squared second. So cancel out the Kelvin, your kilojoule, which is your watt, is equivalent to your kilojoule per second. So what left here is your kilogram meter squared and your second. So solving for our latent heat, rate of our latent heat is equals to your proportionality constant times our area times the humidity ratio of your air and your wetted surface times your latent heat of your enthalpy, and by solving of your rate of your latent heat is equal to 0.029412 kilogram per meter squared second times your 0.15 meter squared times 0.00937 minus 0.0134 kilogram per kilogram, so cancel out. So times 2,470,840 joule per kilogram, wherein it comes from the value of your latent heat, which is 2,470.840, which we convert into joule. So it gives us a value of 2,470,840 joule per kilogram. So your rate of your latent heat is equals to negative 43.93 watts. The enthalpy at 13 degrees Celsius is equals to your 36.719 kilojoule per kilogram from table A2 in the book. So we have here your 36.719 kilojoule per kilogram. So for the formula of your total heat is equals to your convection coefficient times your area divided by your constant specific heat of moist air times your enthalpy of your air minus your enthalpy of your wetted surface at 13 degrees Celsius. So we have here your 30 watts per meter squared times 30 watts per meter squared Kelvin times 0.15 meter squared divided by your 1020 joule per kilogram Kelvin times 36,719 minus 63,965. So from your kilojoule, it is converted to joule. So it become 1,000. So solving this mathematically, it gives us a value of negative 120.2 watts. So cancel out your kilogram, your joule, your meter squared, and your Kelvin. So what unit left here is only watts. So letter B, at 20 degrees Celsius, using the formula of the rate of your sensible heat is equals to your convection coefficient times your area times the difference between the temperature of air and the wetted surface temperature. So we have your sensible heat times equals to your 30 watts per meter squared times meter squared Kelvin times 0.15 meter squared your area, and 20 minus 30 degrees Celsius. So it's just the same when you add 273, it gives you the same value when you minus the 20 minus 30. So cancel out your value of your Kelvin here, your meter squared, so it gives us a value of negative 45 watts. So for your humidity ratio at 20 degrees Celsius, so using the table A2, it gives us a value of 0.01475 kilogram per kilogram. So from 20 degrees Celsius, here it gives us a value of 0.1475 kilogram per kilogram. So from looking for our latent heat or your HFG at 20 degrees Celsius equals to, here is your 20 degrees Celsius. For your HFG is equals to 2454.1. So, converted it into joule. So, we have 2,454,340 joule per kilogram. So, solving for proportionality constant is equals to your convection coefficient divided by your specific heat of your moist air, where your CPM is equals to your 1020 joule per kilogram Kelvin. So, by solving, 30 watts per meter squared Kelvin divided by 1020 joule per kilogram Kelvin. So, cancel out your Kelvin and your joule. Your watts here is joule per second, so cancel out your joule. What unit left here is joule kilogram meter per meter squared second. So our answer is 0.029412 kilogram per meter squared second. So solving for our enthalpy at 20 degrees Celsius, we have 57.544 kilojoule per kilogram. So from your table A2 from the book, we have 20 degrees Celsius. Here, we have 57.544 kilojoule per kilogram. So for solving for your total heat is equals to your convection coefficient times your area divided by your specific heat of moist air times your enthalpy of your air minus your enthalpy of your wetted surface at 20 degrees Celsius. So 30 watts per meter squared times your Kelvin, 30 watts per meter squared Kelvin times 0.15 meter squared, cancel out the meter squared, divided by 1020 joule per kilogram Kelvin. So times 57,544 minus 63,965 kilojoule per kilogram. So it is not kilojoule, it is joule per kilogram. So cancel out the joule, the kilogram, and the Kelvin. So it gives us a value of negative 28.33 watts. So at 28 degrees Celsius, solving for our sensible heat equals to your convection coefficient times your area times the difference of your temperature of air and your wetted surface temperature. So 30 watts per meter squared Kelvin times 0.15 meter squared times 28 minus 30. So Kelvin cancel out your meter squared. So what unit left here is watts. We have the final answer is negative 9.0 watts for our sensible heat. Next, solving for our latent heat. So from the humidity ratio at 28 degrees Celsius, so from the table also, table A2 from the book, we have 28 degrees Celsius, which is 0.02422 kilogram per kilogram. So we have your latent heat at 28 degrees Celsius. We have 28 degrees Celsius, your HFG, which is 2435.2, converted into joule per kilogram. We have 2,435,390 joule per kilogram. So from your proportionality constant is equals to your convection coefficient divide your specific heat of moist air, which is 1020 joule per kilogram Kelvin. So we have here your HD equals to your 30 divided 1020 is equals to 0.029412 kilogram per meter squared second. So solving for our latent heat, we have equals to your proportionality constant times your area times your humidity ratio of air minus your wet humidity humidity at wetted surface at your 28 degrees Celsius. So, times your latent heat or our HFG. The latent heat, rate of latent heat is equals to 0.029412 times 0.15 times 0.02422 minus 0.0134. So, times your HFG, which is 2,435,392 joule per kilogram. So, our latent heat is equals to 116.3 watts. So, next, solving for our H1. For our enthalpy at 28 degrees Celsius. We have here 89,952 joule per kilogram. So, from table A to 2. So, solving for our total heat, we have your convection coefficient times your area divides your specific heat of moist air times your enthalpy of your air minus your enthalpy at weighted surface at 28 degrees Celsius. So, we have here 30 times 0.15 divided by 1020 times 89,952 minus 63,965. So, it gives us an answer of, for your total heat is equals to 114.6 watts.